In the last video, we defined the column space and null space of a matrix. In this video, we're going to be diving deeper into those ideas and exploring some additional properties of them. Just as a reminder, if A is an M by N matrix, we call the span of its columns the column space of A, and we denote the column space by col A, C-O-L-A. And then if A is an n by n matrix, we call the set of vectors x in Rn, satisfying Ax equals 0, the null space of A. And we denote the null space by NULA, so null A. So this is the set of solutions to the homogeneous equation Ax equals 0. And then we're going to add an additional definition. So we say that the rank of a matrix A is the number of pivot positions in A. We denote that by rank of A. We're going to see how that connects to these ideas of column space and null space in this video. To begin, let's explore a few examples. So let's start with this 3 by 3 matrix A, 1, 2, 3, 2, 4, 6, 1, 1, 0. And we are told to find bases for the column and null space of A. And so the way we are going to do this to begin with is just by getting the reduced row echelon form of A. And so you can do that by hand, of course, or I'm just going to write the answer here. I already found it previously using my computer. So this reduces to 1, 0, negative 3, 0, 1, 3, 0, 0, 0. Okay, and so a couple of things we can tell from this. First of all, it has 1, 2 pivot positions, and so that tells us that, going back to that last definition, the rank of this matrix is 2. So that's something just to take note of. But sort of in terms of finding bases for the column space and null space of A, let's start with the column space. So that's going to be the span of the columns of A. So we already sort of have our span. We need a linearly independent set that spans that same space. And so one thing you can think about here is that since the first two columns have pivots, if I were to think of those first two columns as kind of the coefficient matrix of this system and kind of augment them with the third column, I could draw that vertical line in. What we could see here is that we kind of have shown that the third column can be written as a linear combination of the first two columns. So if I call this V1, V2, V3, what we have here is the fact that negative 3 V1 plus 3 V2 equals V3. And you can double check that. Negative 3 times 1, 2, 1 plus 3 times 2, 4, 1 equals, negative 3 plus 6, so that's 3, negative 6 plus 12, so that's 6, and negative 3 plus 3, so that's 0. So it does, in fact, work. And so what we can tell is that these columns themselves are not linearly independent, but because V3 can be written as a linear combination of V1 and V2, but V1 and V2 are linearly independent. And so we can get a basis for col A is going to be the set consisting of just the first two columns, 1, 2, 1, 2, 4, 1. Okay, we want to eliminate that third column since it is a linear combination of the first two. So the set of all three is not linearly independent, but just the first two is. And so kind of the general strategy here is we can get the reduced row echelon form to identify the pivots and kind of recognize, okay, we have pivots in the first two columns. Therefore, the first two vectors in the first two columns of the original matrix A, those two vectors will form a basis for the column space of A. And then in terms of the null space of A, we can take just get rid of that. Let's take the reduced row echelon form again, kind of going back to that. So we see we still have those two pivots. So that's an indication that if we were to augment this, maybe I'll do it for this example. I'm not going to always necessarily do this, but just as we're getting the hang of this, we would augment this with the 0 vector to get solutions to ax equals 0. And so if x is equal to x1, x2, x3, then we could see x3 would be a free variable. And maybe let's erase this so we can work in this area. So we have that x3 is a free variable. We have that x1, minus 3x3 equals 0. So x1 equals 3x3, x2 equals negative 3x3, and x3 is a free variable. So we'll just say that equals x3. So our solutions to ax equals 0 will take on the form x equals x3 times 3, negative 3, 1. So they're the span of that single vector. That single vector itself would form a linearly independent set. So therefore, basis for the null space of A would just be the set consisting of that single vector. Okay. Let's try another example. So another 3 by 3 matrix here. Let's row reduce this. Again, you could do this either by hand or using your calculator or Sage or that linear algebra toolkit I've shown you. However you do this, you would find that this actually row reduces down to the identity matrix. So that's an indication that these 3 vectors are linearly independent. And so those 3 vectors would form a basis for the column space of A. And so basis for call A in this case would just be the original 3 columns. 0, 2, 2. Okay. You could actually, at this point, recognize the fact that since we have a basis of 3 vectors in R3, thinking back to some other videos we've seen in earlier sections, we know that any 3 linearly independent vectors in R3 will span all of R3. So actually, the column space of A just is R3. So if we're looking for a basis for the column space, you could take any basis of R3. So you could take sort of the standard basis, 1, 0, 0, 0, 1, 0, 0, 0, 1. You could take these 3 vectors. I think, just to sort of keep consistent with our process for these particular examples, it's nice to go back to that original matrix, but any 3 linearly independent vectors would work here because we're really just looking for a basis for R3 in this example. I'll go back at this point actually to this previous example. The column space here is not all of R3 because we only have 2 vectors, right, in our basis. So these are 2 linearly independent vectors that would form a basis for the column space of A. So the actual description of this column space is going to be the span of these 2 vectors. In R3, that's going to form a plane. So you could, sketch these 2 vectors in R3. Do my best sort of little sketch here. So you'd have these 2 vectors kind of coming out, however they're coming out. And then if you were to sort of draw the plane, I'll try and extend it a bit. Right. So the plane going through that contains these 2 vectors would be their span. And you could come up with the specific formula for that. There's a few ways you could do that. We don't focus too much on that in this class, but in terms of this class, probably the easiest way would be to row reduce this matrix augmented with some XYZ and focus on what's going on with this right-hand side, and then you'd get a row of zeros at some point. So you would just set that equation, whatever you had on the right-hand side, equal to 0, and that would be your equation of the plane. If you've taken like a multivariable calculus class, you've probably seen methods for finding a plane that contains these 2 vectors. So in any case, biggest thing to pay attention to here is the fact that the column space is actually just a plane in R3 since its basis contains 2 vectors. Here, the column space is all of R3. What about the null space? So, basis for the null space of A, well, if we augment A with the 0 vector, and again, just for now, maybe I'll do that So you can really see what's going on. And if we're solving ax equals 0, so if x is, in this case, x1, x2, x3, then the fact that we reduced this to the identity matrix basically says that the only solution to this is x equals the 0 vector, that x1 equals 0, x2 equals 0, x3 equals 0. So, the only vector is the 0 vector, so a basis is just going to consist of that 0 vector. And so just a single vector, any scalar multiples of this is still just that vector. If you add it to whatever, it's still that vector. So it is a subspace. The span of just the 0 vector is a subspace of R3. And maybe just to really drive home that this is in R3, we can write it out. So this is the vector 0, 0, 0. Okay. The sort of number of vectors that exist in this space is just one. It's just that single vector, because again, anytime you scale it or add it to whatever, you're just going to end up back at that 0 vector. So something to keep in mind. Let's do one more example here, and then we'll generalize some of these ideas we've been looking at. So in this case, A is row equivalent to, so A in this case is a 3 by 5 matrix, and we row reduce it to reduce our echelon form. We get 1, 2, 0, 1, 3, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0. And again, I did this in advance using the computer. You can, do this by hand if you want to practice your reduction. You can use your computer, your calculator, whatever you're comfortable with. In any case, you should row reduce it and get this reducer echelon form. We would identify those as the two pivots. And so what we want to do is go back and sort of find those in our original matrix, and kind of more importantly, recognize the columns that they are in. Again, any columns that do not contain pivots, we could think about, augmenting. Well, you could see actually that the second column is just twice the first column. So that's not going to be necessary when we're looking for a basis for the column space. And then if we were to sort of augment that fourth column, we could see that it is the sum of this 1 and this 1 tell us that it is just the sum of the first and the third columns. So you could see this 1, 3, 2 is the sum of 1, 2, 1 and 0, 1, 1. And then that fifth column, that 3, 7, 4, if we were to think about augmenting with that, is 3 times the first column, so 3v1 plus the second column, plus the third column, plus v3. So you could try that 3 times this plus this should give us this. And so we don't need anything except for the first and third columns to get that same span. Those are the only two columns we need to get our linearly independent set that spans the same space, and therefore that is our basis. So basis for col A will just be 1, 2, 1, 0, 1, 1. And so the rank of A is the number of pivots, which is 2. What you should also notice is that that is the number of vectors in the basis for the column space. And we're going to generalize this in a minute here, but just to point it out. And then what about our null space? So let's call this x1, x2, x3, x4, and x5. If we were to augment that with the 0 vector, okay, then what do we see? We have that x2 is a free variable. So we have, let's just write this out, x1, x2, x3, x4, x5. So x2 is a free variable. Any of these columns without pivots are free variables. x4 is a free variable. x5 is a free variable. And then x1 equals negative 2x2 minus x4 minus 3x5 And then x3 is going to be minus x4 minus x5. Okay, so x equals x2 times the vector -2, 1, 0, 0, 0, plus x4 times the vector -1, 0, -1, 1, 0, plus x5 times the vector -3, 0, -1, 0, 1. So the null space here will be spanned by these three vectors, right? It's, literally written out as the set of linear combinations of these three vectors. So, that's a good starting place for our basis. It does turn out that those will be linearly independent as well. And just sort of the nature of how this row reduction works and how these, this parametric form works, you would be able to prove this fact that when you write out this parametric form, the vectors that you end up with are going to be linearly independent. And so a basis for the null of A, I guess we've been doing kind of this colon notation, is going to consist of those three vectors. So -2, 1, 0, 0, 0, -1, 0, -1, 1, 0, and -3, 0, -1, 0, 1. So there are three vectors in it. And so, the interesting thing here is that we use the pivots to sort of determine both of these. And I think this example really shows that off, where the columns that contained the pivots helped us figure out our basis for the column space. And then the columns that did not contain pivots ended up to be columns that corresponded to our free variables for the ax equals 0 equation, which helped us find the basis for our null space. So that's going to bring us to the next proposition, the next set of propositions. So proposition 359, if A is an M by N matrix, then call A is a subspace of Rm whose dimension equals the rank of A, right? So a reminder, the dimension is just the number of vectors in a basis. And so, we can go back to each of our examples. The dimension in this case of the basis, the dimension of the column space of A was 2. So the dimension, fill that in here. Let's give ourselves a little space. So the dimension of col A was 2, and we're going to need this in a minute. So I'll write it. The dimension of the null A in this case was 1. Here, dimension of the column space was 3. Dimension of the null of A, in this case, it's just technically 0. If the only vector is the 0 vector, then we say that is dimension 0. Even though there's sort of a vector in the basis, that's a little confusing, but we'd still have, since the entire space is just that single vector, it's just dimension 0. And then we said the rank of A was 2. And we're going to write now, erase that the dimension of the column space of A is 2. The dimension of the null space of A in this case was 3. So we could see in all those examples that the rank of A, the number of pivots, was equal to the dimension of the column space of A. And go back and explore those examples and remind yourself why each pivot gives us a different basis element for our column space. An important note here, in general, a column without a pivot can be written as a linear combination of columns that contain pivots, hence how we sort of get our basis. We determine pivot positions by looking at the reducer echelon form of A. However, the basis for the column space of A comes from the corresponding columns of the original matrix A, not from the columns of the reducer echelon form. So just be careful with that. Sometimes it's not going to matter, but oftentimes it will. So make sure you're finding those pivots with that reducer echelon form, but you're going back to that original matrix to actually form your basis for the column space. And then our null space, so if A is an m by n matrix, then the null space of A is a subspace of Rn whose dimension is equal to n minus the rank of A. So again, if we go back to each of these examples, n is the number of columns. And so in this case, let's actually go back and just do each of these examples. N is the number of columns. So in this case, we see that the dimension of the null space is 1, which is equal to 3 minus 2, the n minus the rank of A, the number of pivots. Here, the dimension of the null space is 0, which is equal to 3 minus 3. And this is one of the reasons it's important to identify this dimension as 0 when it just contains the 0 vector. Here we see that the dimension of the null space is 3, which is equal to the number of columns, 5, minus the rank, which is 2. And then we have this proposition here, which is often referred to as the Rank-Nullity Theorem, which says that if A is an m by n matrix, then the dimension of the column space plus the dimension of the null space equals n, which is, again, the number of columns of A. And the sort of quick proof of this is that the dimension, or outline of a proof, not a real proof, but outline of a proof, is that the dimension of the column space is going to be the number of pivots, and the dimension of the null space is going to be the number of columns without pivots. And so if you add those two things together, you just get the number of columns of A. So this is a useful theorem when we, we're going to discuss some uses of this in future videos and in future sections, but kind of a really nice relationship here that ties a lot of things that we've done so far in the course together.